Okay, so welcome back to Cloud Computing and Big Data Lecture 0, the second part of it, the prologue. So if you want a little bit an informal start of the course, again, to see what to expect from the course, clarify question answers. And I hope the first part already clarified the most questions, how the course operates. So via Canvas, assignments, industry projects, and so on and so on. So the second part here now is the idea of really go again into context. What we mean with all of these buzzwords I gave you as a heading of these lectures, right? And of course, there's very much more deeper. They entail more technologies, more, let's say, details, what really the individual lectures entail, and also how we connect this to some practical topics, really, where you face then cloud computing services or, let's say, technologies and products. Coming to lecture 1, as the name suggests, this is really, again, an introduction. It's a little bit different than the prologue. It doesn't talk about the course anymore, and we will dive in some of the topics deeper. But it also gives the opportunity to clarify base terminology. So things you just have to know. What is a CPU? What's the difference to a GPU, right? Who knows the difference, CPU versus GPU? Okay, should be hopefully in 101 computer. Ingo is here gone, but I hope that is these days teach. This is a very important distinction. We will talk about this again, at least briefly, and then make also the core elements and dots why GPUs are necessary for machine learning, deep learning today, and how it basically also connects to cloud computing offers service that you have in Amazon, Google, and wherever you go. Chances are there's really powerful computing and storage underneath it. We also connected a bit to the history, of course, that we have in cloud computing. It came not out of nowhere. It came out of grid computing that we had at CERN at the time when I was saying I was there, a little bit the strategic director of middleware. So this has a long history, the idea of distributed computing. All what cloud computing was doing it much more in industry, commercialized service offering. So it's an interesting let's say, element. And by far, all of you have now experienced it, how it is growing in the internet. I mean, the early days of Google, of Facebook beta, who remember this, where this was all beta technology, right? Google beta. So you would not use it. You would use Yahoo, a search engine. Now everybody Googles everything. And basically now we YouTube everything. And in 10 years or 5 years, we chat GPT everything also. So basically, this is an interesting thing to see how these applications evolve, while not forgetting that all of that is fueled by cloud computing underneath, right? These are all just services underneath, fueling these technologies, and the hardware is giving rise to it. So this will be lecture 1. Lecture 2 then will be, as I promised, a very, let's say, simple introduction to machine learning. Someone of you that have never heard from machine learning doesn't need any prerequisites, not even much on linear algebra. I mean, a couple of dots you maybe know already, maybe on your math memories, hopefully. But this is an introduction which should be relatively straightforward with some examples. What we will do in order to perform binary classification first with a perceptron learning model. It's the simplest learning model you can have. Actually, it dates back to the 60s, quite interesting, and is a base foundation of deep learning today with a neuron, something we have in the human brain. It's a simplified neuron. It's basically not, let's say, exactly mirrored like the human, but a simplified version of it if you want. You see here one picture on this. So we start with this, and then we'll basically add on to multi-class perceptron. This kind of thing, learning model will be extended more and more, step by step, so that you can basically track this. The reason why we do this is that many of the services you have in Microsoft Azure will offer this in cloud solutions, like logistic regression, for instance, or these simple classification mechanisms are still used a lot in cloud computing offers, and we will make the case when I give you some examples of the AWS. And you see also Jupyter. Again, this will be a technology with us that is really, let's say, indicated by the service character. So you think you are editing a browser, a web browser-like interface with a Jupyter notebook, and I think many of you have basically seen that. But in the back, basically, you can have very powerful computing as well. So this is now the interesting thing, that you can port applications very easily between Google Collaboratory and a very, let's say, cutting-edge cloud provider, for instance. So this is an interesting technology. We will look in Python hands-on as well. Then we made very fast the move to Apache Spark. I mean, some of you know MapReduce, and Apache Spark is, let's say, from Hadoop, the next generation, fueling a lot of cloud service offerings today, used with different types of applications, but these are remaining very important applications like structured query languages or databases, how you put them into the cloud and how you access them with machine learning. Streaming is something we don't do too much in the course, but has something to do with data streams that are coming in from sensor devices, measurement devices, maybe. And then the machine learning library is something we will touch upon, is to make the case again with big data and so on, that this is all scalable, right? So this is an interesting term that we will explore more and more, ending in lecture 4, where you then understand how we can quickly go from 1 GPU to 1,000 and so on in this cloud paradigm. And using these libraries, and these machine learning libraries are done in parallel fashions. They're implemented and parallelized already. Hence, parallel processing, distributed computing that I said at the basic is at the heart of these. If you, let's say, download R, statistical computing with R as a tool, or MATLAB, or many others, scikit-learn, I mean, some people maybe know that, scikit-learn is a machine learning package in Python. These are not for parallel processing. So if you throw these to the cloud, it will not work, right? Because they don't use more than 1 GPU quickly. Hence, you need something like PyTorch, TensorFlow, PyTorch DDG, we all cover in the course. And inherent that are then also these libraries, which are already for parallel computing and scalable computing optimized. There are also some graph applications. Some of you know that from Facebook. If you see Facebook, in the end, is just a big graph, right? It's a big graph database behind it and so on, with likes and links between all the different nodes and entities. We will talk about this briefly in the course. We had last year one on social networking and so on. We had dropped this year because of large language models, but you can still look at 2024 if you have interest to look at these. And this is basically a groundbreaking technology, Apache Spark, which is in almost all cloud vendors today, including also Google, which is somehow here missing, Google Proc. But this is also important to know. It's basically cloud computing technology. Then it's time for a little bit of a conceptual review. So we have done machine learning a little bit, so understanding why we want to learn from big data and why we need lots of computing. So now we have to conceptualize a little bit how we actually realize all of that. And we come quickly to something called virtualization. Did you use images, VM technologies already? Virtualization, some of you. Should be also in 101 computing. But don't worry, we also don't need to do too much of it. It's just important to understand that virtualization is fueling a lot of these ideas of data centers today, right? And this is an important factor also for scalability. So scalability is a term we will conceptualize there, where we then really think that you're starting to grow, maybe collecting data like apps, right? So if you have maybe something like Angry Birds or so, and you are a little small startup and failing with a computing game, which was a soccer game, and then suddenly you start something with Angry Birds. Funny enough, they were, let's say, not successful in the beginning, but suddenly Angry Birds, bam, was a huge success. But with this, the users skyrocketed, the data skyrocketed, and this is scalability, right? To take the users with you, right, on this. Now everybody plays numerous apps on Angry Birds, there are even movies about it and whatever. But this was successful to this operation to do this. And we will talk again and again in this course again about these application examples. Again, how this is then fueled by, let's say, price offerings, because of course you see now Google Docs, you use this probably, or Google Collaboratory for free, Facebook for free, the ads and so on. But how is the money coming in? Right? And we will learn something like pay-per-use. Have you heard this? Pay-per-use, perhaps? Subscription models, I guess, right? If you have more advanced cloud services, you usually have 30 days free and then swipe the credit card. That's usually the model, right? And so we talk a little bit about this and how this also affects service level agreements and so on. Hence, we look a little bit how Google data centers operate, Facebook data centers, and video data centers operate. We have also one player here in Iceland where we will try to visit. So this will be one opportunity for you to touch metal, as I say, so that we go at Korputorp, that's here a bit outside in Reykjavik, or I should say Mosfellsberg for the locals. where we usually every year go in every course and touch metal in the sense of we go really inside and you see the real racks, right, standing in a data center. It's still a small data center, not like Google and so on, but it captures the essence of racks, of the air cooling, the sound that you have from the many, many, many GPUs operating the second floors, all the kind of infrastructure you have. We will organize this as a trip, and we will have an invitation there during the course so that you get a better meaning how really a data center looks like from inside. Then in lecture 5, we go back to deep learning and connect the dots we left with a perceptron, basically the simplest learning model, if you want, this linear learning model. And now basically go bigger and bigger by using this single ingredient that we model as a neuron and connect many neurons in many layers together, and go quickly from artificial neural networks to something we call deep learning. Hence, there will be some foundations, artificial neural networks, backpropagation of errors or some learning algorithms, but also we keep that to a moderate degree in order to understand a little bit how deep learning works. This will be not so much, let's say, cloud computing in the sense it is more rather introducing, different models, different technologies. What many people know is things for image analysis, like convolutional neural networks, autoencoders. But we use, for instance, also long short-term memory, gated recurrent units, many of the, let's say, deep learning models for time series data, which are not images, for instance, and so on and so on. So it will be a sort of foundational lecture to understand deep learning better, because some of the industry partners will ask you to work with them in deep learning, right? So hence it will also have relevance for the industry course. Hence we put it also more and more early in the course. To give you some examples what you can do in deep learning, we lose a little bit something out of our research in remote sensing as examples of cutting edge learning models where we really use 1,000 GPUs in parallel to understand data, to learn from data. And then, of course, also some sequence data that is text, but also, let's say, measurement, numbers, values, measurements of any kind. So this is something where you understand we have always these different types of data, hopefully, and you have specific learning models for it, right? And this is sort of the difference between, you would say, maybe this term deep learning of saying just different neurons. You would have different type of architectures of deep learning used for very specific problems, right? And this is something which is also fueling large language models, autoencoders, and so on. And we will talk about this in lecture 6. Also connect the dots a little bit why computing power is, of course, essential in these. And basically, this would be not possible, the large language models would be not possible without cloud computing, GPUs, and the computing we have today. Hence, there's something we call about parameters that we will review in deep learning. The learnable parameters, they will grow and grow. The bigger the model, the more parameters to learn, the more computing power you need, basically. And this has, let's say, the major impact that we know these days in large language models, right? You have used some of this in ChatGPT. What you don't know is maybe here's some of the examples you see out of our research when we have here, 7.8 billion parameter model. This is not obvious to you. We see how that materializes when we start from neural networks very small with thousands of parameters to large language models we have today with 7.8 billion and more actually in GPT-5 and so on. Hence, this will be nicely an example of generative AI. So large language models are one example of it. But of course, as I said, we will do a couple of other examples for images, videos, and so on as well. And also connect the dots why it's important now for AI factories in Europe to offer this to public sectors. I mean, you are basically the first wave that will encounter this in all public sector organizations all over in Europe, that you will have not only chatbots, but automatic filling of forms, large language models doing all your tax reimbursements and stuff like this. So many of the services from the public sector to save costs will be transformed in AI. Right. And of course, this has also dangers, as I was alluding to with hospitals, for instance, right? Giving our medical data out to some cloud vendor somewhere in US, it's something we don't want. Hence, there are also lots of AI laws and AI acts, GDPR, different law mechanisms in place where the AI factories in Europe will be then taking place in order to protect us maybe from other, let's say, non-Europe solutions. This will be also a theme in this, but of course, we will always take the most impact into the technology, right? I'm not a lawyer. I just say you there's an AI Act. We cannot do everything with the data and so on. We are protected here and there by law, but this should be also mentioned in that particular point. So this is a new lecture. I hope that will be attractive. It has lots of news of AI, cloud computing, and specifically generative AI. Much interestingly enough, this is a more traditional model, MapReduce, but I have seen many of you know that already. And it's also no wonder because it basically reflects a paradigm in 101 computer science again, divide and conquer, right? So here we're talking now, interesting enough, not necessarily about the training of the biggest perfect model that we have seen in the large language model. Here we talk about the throughput. So we want to very quickly go through a very big bunch of big data, right? And how you would do this if you now have, let's say, very many newspapers, and you want to say, okay, we have this many stacks of newspapers, and we want to have all on political sciences extracted and looked at if a particular president is done, and mentioned. How we do this in the class? Any idea? We would divide, right? So I'm not interested in looking through all this pile alone. So I will give you 100, 100, 100, 100, 100. And this is a problem which is not connected during we look for that article in political science, right? So this can be done independently, as we call it. That's why it is independent parallel. And this is different from machine learning, deep learning, where we massively parallel update the gradients of learning every time step, or weather prediction. The weather next to us, left and right on the GPU's coordinate, affects me in my coordinate. That's why basically in the high performance computing course, and in these, you need this kind of high performance interconnect. Here we talk about MapReduce is really something, you have a big problem like the newspapers, we distribute it on all of us. And then we collect just the results back in the conquer step and say, okay, how many articles were the political science? How many political science? What the president mentioned? Okay, and then we have the result and report it. By this, we have lots of time gained rather than one is looking through it. Hence, there's a sort of scalability again of these so-called workers, right? Of course, if you have a very big problem, our class might be not enough. So we should maybe have the class fellows from our other professors. This is, of course, an analogy, right? Now, if you have something like a company and you basically growing your data pile more and more, then you basically have the trouble that maybe transporting your data is also a problem, right? So this is a paradigm, MapReduce, we will learn, that is a bit data-centric, put the computing to the data, small high throughput computing tasks, summarizing, identifying patterns, and so on. And we will have some applications for it. And by famous implementation is Hadoop, but Apache Spark is basically the kind of next transition to it, and we will also make the case for it. Then back to more conceptual topics. As I said, we put the practical topics first with big data and so on that we use in the industry projects, and the infrastructure as a service is now something where you talk about plain metal provisioning. That means the computing is there. You maybe have some virtualization layer on it, but no big services on it, right? So this is in cloud computing called the infrastructure as a service level. You would have computing entities, they're virtualized, but you can still switch many of them on and off to a problem. By this comes this idea of cloud, right? The scalability. The cloud is, a big cloud, a small cloud, big cloud. You can basically justify the amounts of computing very flexible, and also adjust this with resource sharing. And the same is true, as you see there, for different storage options. Hence, this coined the term cloud computing, that on demand, you can have computing tomorrow by swiping the credit card much more than, for instance, buying your own computer, maybe a high-performance computing machine down in your cellar with 6 GPUs. When your 6 GPUs are fully used, but you need more, you just cannot just buy 3 or 4 more, get them into the system for tomorrow. In the cloud, you can just order more 4 GPUs tomorrow, the day after, 8 GPUs, and so on. So this flexible computing model was basically coining this cloud computing term in the beginning. On this lowest layer, you can have infrastructure as a service, a basic infrastructure of computing storage. We will talk about this. What then will happen is the platform as a service level, which was much more oriented towards developers. And in computing, when you create an app, and we will talk then about app design and apps. Now, if someone is in app development here, Do you do some apps? I know maybe software engineers do this these days. So we learn a bit how you do this in the cloud, basically with a development cycle. We're using the infrastructure as a service components with some services, and that's where the service idea comes again in. So you have some computing elements which are always the same in computing games. For instance, a charging module, right? Swiping the credit card is always the same, no matter if you do Angry Birds or another game. Somewhere must be some functionality in software to charge people and to get the credit card. So there's a platform approach to it. You need basically something else that you also want to have in this. Maybe kind of storage that you put in, user data for a game, for something what you have, and in a flexible manner. So the Google platform we're going to use there as an example, that you see that the platform as a service level, which is a little bit higher than essentially the infrastructure level, gives you distinctive services to really leverage the cloud, but it's not really completely user-facing in the sense of, just swiping the credit card and use software. This would be rather the idea of then the last layer. And in the lecture 1, we connect this all a little bit together so that you see that infrastructure as a service, platform as a service, and software as a service is the highest now of the ideas of services, is where you don't think about any development anymore. You just use what's existing. But of course, this often comes for a price, maybe indirectly by watching ads or swiping the credit card that you already know from Zoho projects or Google Docs. I think you know the game from Facebook and others. So this is all examples of software as a service, but, and that's now the point, they use platform as a service and infrastructure as a service components for all of their offerings, right? It's not just visible to us because as user, we're not interested in that. But of course, when we do Google Docs, when we edit our Word document and then suddenly 20 and 40 people edit it for a proposal, maybe, or whatever we do in science, or you basically as assignments growing, you want to have good performance of this. So they automatically add more computing and more storage if needed. So these are all concepts where essentially this was perfectly flying. Also think about back in times where, we had really software shops. I'm not sure, you probably didn't experience that anymore. But, when I was young, I had game shops where we go in and get a CD or something. And not even a CD was not there, it was discs, right? Monkey Island and whatever. So you have 30 discs, go to a shop and you get a package and that was your software. Now everything is online, right? You basically just get everything, what is it called, Steam, right? And then you go to Steam, you get your game, you basically download everything from the internet. Also, that had lots of implications, the online game worlds and so on. Scale with the amount of users, right? A good example is CCP games here next door. They have a kind of space game. Maybe it's good to look at this once. But they have to also have intrinsically the scaling of users again. And this is also where software as a service and the underlying platform and infrastructure as a service were skyrocketing in really making the software working. Coming back then a little bit to the benefits of scalability, also for data analysis, for analytics, as we call it, is basically the data analysis on steroids, a little bit combined with, you would say, cutting edge technology like MapReduce, maybe frameworks that enable it, or PyTorch and others. And we will have some, let's say, easy applications that like shopping basket analysis. Here, diapers and beer, they're always bought together. We will find out why this rule exists in shopping basket analysis, but also simple data mining algorithms like clustering. You see here basically a kind of point cloud from an inner city. When you cluster this with cluster algorithms, then you come back and can reconstruct whole cities or countries. You see the Netherlands here as a point cloud, remote sensed. And you can recluster this by clustering algorithms, data mining algorithms, as they're called, by having back buildings. Now, the point is that this is so much data that you cannot do this on a laptop, right? You have to do this in the cloud with high performance computing and much, much more computing needs. Also, when we come to recommendation engines, I mean, all of you know that by now. I think Amazon, if you buy something, right? And now I'm not talking about the Amazon Web Services, but the Amazon bookstore is not anymore just a bookstore. But also their success was largely their AWS they had internally and then exposed to basically people, a cloud infrastructure, right? So Amazon, in a sense, was not really a bookstore. It was a cloud company before. And then basically via the bookstore and via the scalability could now do everything. And this was all fueled by this infrastructure that you have in this cloud. Very interesting ways also how this was fueling basically the concept of technology evolution, because money was available to really advance in technology, like GPUs, right? Many people buy more and more GPUs. That means NVIDIA gets more money to do more exciting things, more specified chips, and so on. We will talk in the course as well. Now, switching perhaps a little bit the view, when you now talked about how we use the cloud, what are machine learning algorithms in the cloud, this is one step further where you maybe also think about management already, right? If you have maybe a job later as a software consultant somewhere here in Iceland or wherever in Europe, and they will say to you, we have 5 people doing data analysis on our data all the time. They have always the same requirements. They need these and these tools, these and these data. Perhaps you containerize their applications on an infrastructure, might be an internal cloud or an external cloud. These are all terms that maybe don't mean anything to you, just individual, but we will see how that materializes when we come to this. That means that basically a very simple approach to have all the right tools and data available exists, and you can nicely shift them. So if you have a Docker image, basically you can shift them between Microsoft Azure, then to Amazon. They're all based on Docker. So you can basically shift then the services and the offerings, a bit counterfeiting, if you want, the kind of vendor lock that you have sometimes in these cloud offerings, right? If you have your management on these applications containerized or based on these technologies, chances are that you much easier can prevent a vendor lock, which is important. So let's say with one of your cloud vendor will go bankrupt, then basically everything is lost what you create for them very specifically, or they're getting too expensive for your company, right? So this is an approach basically where you can see you can quickly move to another cloud vendor, where this comes again as a very handy tool. And there will be lots of details we talk about. There's Uptainer. Some people may know it from Singularity in the past. It was another Docker-like, let's say, containerization technology that now switched to Uptainer. But in the end, they enable the same and are often also deployed on our HPC systems. So that's why we also talk a bit about Uptainer. It's a bit less common in real cloud vendors. So AWS, Google, and MS Azure are rather built on Docker and Docker Hub and existing images and so on. We will learn about this, that there are also lots of services around that in the public cloud vendors, right? So hence, when you become a cloud engineer or so in a company, then chances are that you use many of these services. Then as a very, let's say, advanced, because we're approaching the end of the lecture, this lecture 14, at the end of the course. This is an advanced topic for machine learning. I basically already motivated this a bit in the beginning, where I said the performance of what you have seen by now, machine learning, deep learning, everything is largely driven by the fact of so-called hyperparameters, right? The best model has no chance if you have the wrong learning rate. And learning rate is a parameter, and we have a couple of more, how many neurons are in one layer, how many layers. There are lots of this. What optimization algorithm I use? Do I do stochastic gradient descent, Adam optimizer, whatever? These are all details. But the point is the right combination makes it possible to achieve the best performance. And you as a human can't do this systematically. You just pick some out of your gut. You would say the learning rate will be 0.3. And this has something to do with how the optimization algorithm works, and to really systematically check all of these values, 0.5, 0.51, 0.52, 0.53. And we will show in this lecture that just the difference of a couple of commas can make a difference of 40% performance improvement of machine learning, just because we hit basically the lowest error. So this has something also to do with optimization. We will talk about this. But this is a tool which should be in the pocket of each, let's say, sophisticated machine learning engineer today. But the point to the course is it needs significant computing, right? Instead of you as a human now use all the different combinations, maybe not all the comma values for the learning rate, also the combination with the Adam optimizer, with the SGD, with other optimization algorithms, give you then in the end a huge search space of the parameter set, which is impossible for humans to do. There's some gut, let's say, values you can take from previous running models in machine learning that stand the test of time and have a chance here and there to report already good accuracy, but you can always improve with this hyperparameter optimization techniques. And we have shown though in many, many times. And we're coming actually close to the end of the course. So Fitz, hi Iris, good to see you. Thanks for coming. So some SME partner already came here, and we will have, soon close here with the lecture. Just a couple of things more. AutoML is very related to it. There we talk about a bigger story. It's not just hyperparameters to optimize, basically massaging a little bit, let's say how this simple learning model or the big learning model, whatever in the optimization take place. Here we also change, let's say, layers. We also change the type of model. Maybe, let's say, an LSTM, something for sequence analysis is not good enough. We change a GRU, and this is all automated. Other topics like AutoGluon use foundation models. Have someone already heard foundation models in science and engineering outside? So this is something where lots of data was already trained on basic stuff that is essentially not as stuff related to your problem, but has some basic foundation. So AutoGluon, for instance, is a tool has been trained on all public existing tables somewhere. So this is a foundation models that know tables better than any human could ever envisage. And you use this basic tool to fine tune it to your table and table data you need. Right? With this, you need some computing power, hence the relationship to the course, and of course, good data sets. But this has a chance to report much more accuracy than you could ever do by manually feature engineer and so on, do machine learning data mining. But many of these tools, of course, have the footprint, like RayTune is a very good tool, but it needs computing power, cloud computing, and high performance computing. Then as a last, let's say, formal lecture, I told you in the beginning a little bit, we will, in the structure, change the view now again a bit to the situation that, your boss comes into your office and then will ask you, can we have a cloud in-house? And you build it because you are having trained this at the University of Iceland. And then they will say, well, we need this and this and this, computing and nice storage here, but we don't want to use Amazon, something to the outside, because we have patient data or we have some other bank data, trading data we don't want to expose. Should be in-house, we buy you everything. Now, then you should not start in getting 10 software engineers that reinvent the wheel and create again services and services. You basically say then, okay, I learned about OpenStack. So OpenStack is something which I would refer to like a very big Lego box. I would say Lego is known to everyone these days, yeah? Lego, Duplo, good. So I'm talking about these bricks that you need, right? And today you see Lego evolve to extremely funny bricks, but they might be interesting for something. So hence OpenStack has a large portfolio of already technologies, implemented software you just put together like Lego bricks to create a cloud offering, which is like Amazon or MS Azure for certain parts of the game. Of course, you have to have the hardware still, right? You have to have the own computing, the own storage in-house, but it's still scalable, so you can extend to the number of GPUs you maybe deploy over the next years and so on. So fascinating technology basically to think about how you do it your own. Then we close the course with the epilogue. I already said this is sort of, let's say, a very informal lecture. I sit just in front, show you job description, that all the buzzwords I have in the course, of course, are exactly mirrored to job description. So we also have this in the course. You need to know about Docker. You need to know about, deep learning techniques of sorts. So this will be just a wrap up essentially from 10,000 feet perspective of what you learned. Again, I give you one video as homework. It has another perspective on it. It is fueled by Amazon, and I'm not paid by Amazon, but still it has a good introduction video to really summarize cloud computing again. So I give you this as homework. And as I promised, with each of the lectures you will see, there's lots of bibliography. We said we don't do a book in the course because it will be outdated tomorrow. But there's lots of references where you can always learn more. European AI factories, for instance, that I mentioned, is one part of it, and you go again and again. You find these references mostly in context to each slide, right? And this would be also my recommendation to you here and there. Maybe look down into these references to understand more. And this gives me also the opportunity to do two things. Firstly, I have a large team, many PhDs finished, and a large research group that lots of this material you see on the slides is fueled by their results in the course, and gives me, secondly, also the introduction to Ingolfur. I mean, many of you maybe know him already from some course, but Ingolfur, the floor is yours. Maybe say one 1 minute about you something, and then we come to Iris and SME and so on.
All right. Hi, everyone. My name is Ingólfur Hjörleifsson, and I am a second teacher in this course, first-time teacher in the course, it says. And so I will be leading and assisting you with the industrial project. So the 50% of the course, we will start on Thursday. And we have introduction towards 2 companies. One of them is standing here behind. This is Orb Green or Orb EHF. And they will introduce their project for you, which you can assign up to as a group, 3 to 4 people or 2 to 3 people, depends. 2 to 4, I think, will be a best limit. And there can be more than one group, hopefully, right? And then there's a second company called the Get Ráðgjöf, a retail company in the clouds, and they will also introduce their projects. And the same there, more than one group is available, so 2 or 3 groups with 2 to 4 people per group. And then there are 3 more companies to come, will be introduced the week after, hopefully. And that would be Trouble is one of the acoustic company we haven't yet got notice from, but the Greenfish is the second one, which is more like an image processing using image AI models, etc. So all these groups are using, or this project are using AI more or less in their project, and the cloud or service and Amazon services hopefully as well. So this is a very short overview. Thank you, Morris, and we will see you on Thursday. Be available.
Okay, good. Yeah, you heard Ingólfur, the second basically teacher here, also part of my research group, really an industry specialist. All the testimonials you have seen from the companies, we work on this together, also with many of these ladies and gentlemen you have here, basically that doing then the work with the companies all the time. So we stop here, the recording, and have time, of course, afterwards for question and answers.